I'm very excited today
Enjoy,
to
Jure.
take you back to 2011 Wisdom in Hong Kong, where we presented the supervised random walks paper together with Lars Backstrom, who at that time was building the People You May Know system for friend recommendation at Facebook. So let me tell you how the world looked like in 2011. In 2011, computing was going through a big transformation. Online social networks, blogosphere, social media was just being invented. And already at that time, online social networks had a profound transformation in how knowledge is produced and shared, and how people interacted and communicated with each other. It also immensely broadened the scope of computer science as a discipline and really brought kind of computer science to start having a societal impact. And one of the key questions in the literature at that time was about how do people find friends and people to connect to in these large online systems. And when the large body of work of research was capturing the dynamics of the social network graphs at the massive level, at large scale, the question really that remained unanswered was what links are going to occur next. And here the seminal work in this space was by David Lieben-Noel and John Kleinberg back in 2003, where they were examining various kinds of heuristics and kind of metrics that could predict what links are going to happen in citation networks in the next year. What became interesting as these social systems and social networks became more and more complex, the question was what individual links an individual node is going to create in the future. And the question was whether that even be able to predict that, because many attributes and many factors played, location, school, job, hobbies, interests, all these different multifaceted interactions and interests could lead to a creation of a new edge in a social network. So we were excited to talk about and do research in the field of friend recommendation, where we want to learn to recommend potential friends to a user in a social network. When we actually examined with Lars how links were created in a social network of Facebook, we found out that 92% of new friendships on Facebook happened through a friend of a friend. So basically, large majority, 92% of edges created where there was at least one friend in common. And this is well known in social science, and it goes under the triadic closure framework that was first proposed by Mark Granovetter, and show how important are these triadic closures where links happen with having a friend in common. What was also interesting is also the importance of the social capital theory that we were able to measure on Facebook, where we found out that the probability of an edge increases as a function of number of common friends. And you can see that the relative probability increases by 1,000, 10,000 times, depending on the number of common friends a pair of people has. So this was very, very interesting findings. And the question was, how do we bring in the social network structure captured in these simple metrics, as well as the node features and node attribute information? And we were really inspired by the groundbreaking work of the PageRank and random walks, the PageRank algorithm, which I would say is one of the most beautiful and most impactful computer science algorithms. And the way we can understand PageRank is that PageRank assigns importances to nodes. And the idea in PageRank is that basically the importance of the node depends on the importances of the others who point to it. So there is this voting interpretation of PageRank where each link's vote is proportional to the importance scores of the source node. And every source just kind of sums up the importances of the others who are pointing to it, and then takes its own importance and splits it to the others the node points to. There is also a very interesting second interpretation of the PageRank algorithm, which is the random surfer model, where a random surfer serves the graph and it's at some node u at some point in time. And then at the next time step, the surfer follows an outlink for that node u uniformly at random. And there is beautiful mathematics behind this stochastic process in the graph, in particular the theory of Markov chains, where we can basically say that the PageRank vector P at time t plus 1 equals the Q, the PageRank transition matrix, times the PageRank vector at time t. And if we keep multiplying this vector P with the transition matrix Q, actually this multiplication process converges. So basically the vector stops changing, and P is then the stationary distribution of the random walk. So basically it is a probability that in some point in time in the future, if we stop the walk and look where is the walker, that distribution is captured by the PageRank vector. So we were excited about PageRank because it's a powerful way to capture the network structure. But we also wanted to use node and link features to kind of guide the random walk. So the idea was that we want to combine PageRank with supervised learning. PageRank is awesome at capturing node importances and based on the network structure, while supervised learning is great with node and edge features. So the idea was that we want to do this supervised friend recommendation or supervised prediction, where given a user S in the social network, we want to recommend friends. And the way we do this is that we want to identify a set of positive nodes in the network. These are the people that S is going to create edges to them in the future. And then we also sample some negative examples, negative nodes to which S won't create links. And now we can basically formulate a supervised ranking problem where we want to assign higher scores to the positive nodes, to the green nodes, to the nodes S is going to link in the future, than to the negative examples, the red nodes. And the way we came up with the idea was that we are going to take this unweighted social network, and we are going to learn an edge weighting function, what we call an edge strength function, that is going to put, based on the properties of the edge, it's going to put a strand there. But the idea was that now that we have the strengths, we are going to run PageRank or random walk with restarts on the weighted graph. And then we are going to rank the nodes based on the random walker visiting probability. And basically, in this case, PageRank assigns importance scores, visiting probabilities to every node in this weighted graph. And we are going to recommend top K nodes that get most visited with by the random walk, that have the highest score. And the question is, how do we set the edge strengths? The idea was that we want to learn how to set edge strengths from the node properties such that PageRank is going to correctly predict and rank green nodes, the positive examples, above the negatives. So if we write out the math, we want to learn this edge strength function f that's parameterized by w, that takes the edge features x, multiplies them with w, gives me an edge strength. And the goal is that once we have the weighted graph, we now run the PageRank algorithm on this weighted graph, and we want the visiting probability, the PageRank score of positive examples, positive nodes, to be higher than those of negative nodes. And what is beautiful in this algorithm is that the same way that PageRank can be computed iteratively using the power iteration, but basically taking some random starting vector P and then multiplying it with the transition matrix Q and keep iterating this, also the derivative of the edge strength function W can be computed iteratively. So it means that basically we can take the derivative of the PageRank score with respect to the parameter W that is of the function that sets the strength of the edge. So the cool mathematics that happens in this paper, kind of surprising part, is that you can actually take derivative with respect to this recursive PageRank formulation and actually compute how should you change the edge strength vector parameter function W to set the edge strengths in the optimal way. We have actually experimented with this algorithm after we have developed it, both on publicly available social networks and citation network data, as well as on the real Facebook graph. At that point in time, we took the graph of Iceland that was it was kind of small, to 174,000 nodes, about half of the Iceland's population. Every node on average had about 168 friends, and people were very active at that time by adding new friends. an average person added 26 new friends in a month. And we said that the edge is going to be positive if on November 1, 2009, it's going to be added in the next month and a half. We described every node with very simple features like age, gender, and school they attended. And we also put features on the edge, which is age of an edge, communication strength, profile visits, and the number of contact photos. And then we run our supervised random walk approach to actually try to learn those edge strengths and then rank all the nodes in the graph and see if we can rank the positive nodes above the negative ones. And what was interesting is that we were able to do this quite successfully. We were able to do this better than what common heuristics would do, as well as decision tree and logistic regression baselines, where we did quite a bit of feature engineering. The interesting thing is that basically we were able to predict 7.6 friends out of the 20 that a person would add. Interesting to this work, it actually had quite big scientific impact. It received about 1,300 citations till today, and it was basically one of the first ideas to, in a coherent way, kind of in a unified way, combine node attributes as well as network structure information into one supervised predictive problem with basically no network feature engineering. So in some sense, we can see supervised random walks as one of the precursors of the modern node embedding algorithms, especially deep walk and node2vec, which are also both random walk based, that they further basically extended these ideas, as well as graph neural networks are another kind of consequence with similar type of thinking. What was also interesting is that we actually have implemented some of these ideas in a production system at Facebook, where we were recommending friends to users. And this had humongous impact at Facebook. We found out that we were able to predict about 8 friends out of 20 correctly in the future. And the improvement above the previous Facebook's People You May Know system was 2.3x. So the fraction of friending based on these recommendations drastically increased, which also then accelerated the engagement of the users and accelerated the growth of the Facebook as a global social networking platform. So let me briefly conclude and make some reflections. Right back in 2011, that's 12 years ago, large-scale network data just became available. And there was this amazing opportunity for large-scale network analysis. And the benefits of working with massive data started to be shown because we were able to observe patterns that at small scales in small data were just invisible. Another important aspect was that there was a lot of interesting networks and graph theory questions, both in computer science as well as more generally. The importance of scalable algorithms and models actually started really to show up. What was also interesting is that at that point in time, we started to realize that social networks implicit between humans for millennia have started to be recorded in our information systems like Facebook. And that's meant that software started to get a complete trace of our activities and increasingly knowing more about our behavior than ourselves. And it started to show, and we started to realize that models based on algorithmic ideas turn out to be crucial in understanding these types of developments and really making these large-scale information systems useful. So again, thank you so much for this recognition. I hope you got the idea of this work and the time in which it was developed. And thank you very much.